These two bottles each contain a solution of Allura Red. Allura Red is also known as red dye number 40. It's just red food coloring. But there's a difference in how intense the color is, or how dark the color is between the two bottles, and that difference is due to the concentration. We would say that the bottle on the left is concentrated versus the bottle on the right is dilute. And I want to make the connection between the terms concentrated and dilute, which are relative. The one on the left is concentrated relative to the one on the right. And molarity. The one that's concentrated has a higher molarity, and the one that's dilute has a lower molarity. So if we were looking at numbers for the molarity, the number for the concentrated solution on the left would be a bigger number than the number that we would get for the molarity for the solution on the right. And when I say relative terms for concentrated and dilute, those only make sense in the context of comparing two things. Just like I could say that I'm tall compared to a kindergartner, but I'm short compared to a professional basketball player. Those are relative. In an effort to reduce packaging waste, some refills are available in simpler packaging, and sometimes the refills are more concentrated than the original solution that we bought. And a great example of this is Windex. Windex is normally sold in a spray bottle, and it has a kind of a characteristic bright blue color. And all of the chemicals that really go into making up Windex are actually colorless, but it's probably a good idea to make household chemicals have some color to them, just so that nobody is ever tempted to confuse them with water. And so if you go to the store, you might be able to find one of these concentrate packets. And the idea would be that you would take the contents of that concentrate and pour it into an empty bottle, and then fill the rest of the bottle with water as you dilute it out. And so my question for you here with this slide is, how would you expect the color of the concentrate to be compared to the color of the original Windex solution? Think about that for just a moment. Pause the video if you need to. Okay, so when solutions are colored, the darker solution is the concentrated solution, and the lighter solution is the diluted solution. So the regular Windex is the diluted, the concentrated refill is the concentrated solution, and so it would be darker. That refill is going to be darker than the original. Another way that we can use molarity is as a conversion factor in stoichiometric type calculations or dimensional analysis type calculations. In order to do that, we have to understand what the molarity means, right? 12 molar HCl means that 1 liter of solution contains 12 moles of HCl. That goes back to the definition of molarity. Molarity is moles of solute divided by, or per liter of solution. Per means for 1. So if we have 1 liter of solution, we have 12 moles of HCl in this case. So whatever this number is for molarity, that number becomes the number of moles of the solute that we have in 1 liter of solution. So we can build a conversion factor, right? The idea with these conversion factors is that these are the second fraction. These are the things that we multiply our given times. And we'll set it up so that whatever units we're given go on the bottom of our conversion factor. So if we were given liters of solution, we would put 1 liter of solution on the bottom. If we were given moles of HCl, we would put 12 moles of HCl on the bottom. And then the other piece would go on top. In this example, we can use molarity as a conversion factor. The problem asks what volume in milliliters of 15 molar aqueous ammonia solution contains 0.115 moles of ammonia. Now you absolutely can work this problem by going back to the definition of molarity, that the molarity is equal to the moles of ammonia divided by the liters of solution, and the molarity is the 15, and the 0.115 moles is that numerator, and what you're solving for is the denominator. I'll let you do that math on your own if you'd like to work the problem that way. Now, what I'm going to do instead is work this as dimensional analysis. And with dimensional analysis, I'm going to interpret the molarity. Try that again. I will interpret the molarity as meaning that 1 liter of the solution is equivalent to 15 moles of ammonia. So that equality right there is what I can use to build the second fraction, the conversion factor. So the only other number in the problem is 0.115 moles of ammonia, so that's what I'll start with. There's my given, 0.115 moles of ammonia, and I'll place that over 1. I know that I want to put moles of ammonia on the bottom of the next step. And according to this conversion factor we just wrote out, I've got 15 moles of ammonia for every 1 liter of the solution. And so if I run that through a calculator, I'm going to have 0.115 divided by 15, and that works out to be 0.00767 liters. That's really kind of a small number, and the problem actually asked us for milliliters. So to go from milliliters, or from liters to milliliters, I would multiply by 1,000. That's basically just moving the decimal point 3 times. 1, 2, 3. So if I convert that to milliliters, we'll have 7.67 milliliters. This example asks us to find how many grams of table salt need to be dissolved to make 1.5 liters of a solution with a concentration of 0.15 molar. All right, so how do we get started on this one? Well, I guess first of all, table salt. What chemical compound is table salt? Well, let's see if I can find my pen. My pen doesn't, oh, it got disconnected when I took a break here. All right. That should be working now. Table salt is NaCl, sodium chloride. And let's see, molarity is probably going to be a conversion factor. This means that 1 liter of solution will provide 0.15 moles of salt. All right, so with that equivalence, we can put 1 piece in the bottom of the conversion factor, the other piece in the top. So the number it looks like we're going to start with is 1.5 liters of solution. Okay, so 1.5 liters of solution is our starting point. We'll place that over 1. And then with our molarity conversion factor, we need to put liters of solution on the bottom. So that will be 1 liter of solution, just coming from the definition of molarity, and then 0.15 moles of salt will go on the top. And if we multiply that out, that's going to be 1.5 times 0.15. That's going to give us 0.225 moles of NaCl. So that's just using the definition of molarity to figure out how many moles of salt are in 1.5 liters of solution. So we're close. We've got salt, the chemical we want, but we were asked for grams. So we're going to have to do another conversion. We'll start with the 0.225 moles of salt, and we need to convert moles to grams. That's a radiation sign conversion. Put moles of salt down here, and then grams of salt in the top. So on the radiation sign, the number that goes with the unit mole is 1, and the number that goes with the unit grams is the molar mass. So if we're going to find the molar mass of NaCl, on the periodic table, sodium is 23, and there's just one of them, and chlorine is 35.5, and there's just one of them, and that adds up to be 58.5 grams, or grams per mole, depending on how you want to write that. So in our conversion, we'll put in 58.5 grams. Now if I run that through my calculator, I end up with 13.2. And moles cancel with moles, so we've got grams of NaCl. So in order to make 1.5 liters of 0.15 molar aqueous NaCl, we would have to dissolve 13.2 grams of salt in enough water to make 1.5 liters of solution.